So to find dy dx for this one, we have to do it implicitly because of all the x's and the y's. All the y's, you can't just solve for y. So we'll take x squared y to the fourth first. That's a product rule. So it'll be x squared and then times the derivative of y to the fourth, which is 4y cubed, dy dx. And then plus, and then y to the fourth times the derivative of x squared, so 2x y to the fourth. And then for the next one, it'll be y cubed times x, product rule, so y cubed times the derivative of x, and then plus the derivative of the y cubed, which is 3y squared dy dx times just the x. Everybody good with that first half of it? Everybody good so far?
Yeah.
Okay. And then the 2xy, we'll treat the 2x as its own function and the y as its own function. So we'll have 2x times the derivative of y, which is dy dx, and then plus the derivative of 2x, which is 2 times the y. There's a product rule on that one, and then minus 1 at the end.
Would we not have a y cube? Oh, never mind. I see it there and I lied.
Yeah, we got a y cubed right there. So then all we want to do is get everything that does not have a dy dx on one side and everything that does have a dy dx onto the other side. It doesn't really matter which side you move them to. So I'll just move the dy dx stuff to the left and everything else to the right. So I'm going to rewrite some of these. This is 4x squared y cubed. This one is 3xy squared. And I know I'm leaving off the dy dx's right now, but I'm going to also subtract the minus 2x over here. And those all those terms had a dy dx in them. So I'm just multiplying them all by dy dx. And then on the other side, I have a 2y minus a 1 already. And then I'm going to subtract a 2x y to the fourth, and I'm going to subtract a y cubed. Then I'm just going to divide by what's in the parentheses there and get 2y minus 1 minus 2xy to the fourth minus y cubed over 4x squared y cubed plus 3xy squared minus 2x. Everybody okay with that one? Any questions on that?
Just making sure when you take the derivative of a y value, that's when you put the dy dx, right?
That's correct. Anytime, so we're taking the derivative with respect to x. So anytime we take the derivative of any variable that is not x, we have to add in a dy dx or a d. You know, if it was like suppose it wasn't a y, suppose it was like a z, then we'd add in a dz dx. Or if it was like a theta, we'd add in a d theta dx. But yeah, most of these will usually just have y's. Does that make sense or no? Does that answer your question?
Yeah, thank you.
Okay, cool. All right, so let's move forward and do a little bit more of this. We're going to actually skip this. That's not necessary. Let's see if we can find all of the vertical tangent lines for 2x minus 3y equals x squared minus y cubed. So to find vertical tangent lines, that means we need to find places where the derivative is what?
Undefined.
Undefined. So first off, we need to find the derivative. We need to find dy dx. So take the derivative of the left-hand side with respect to x. Should give us what? Should give us 2
dy dx.
2 minus 3 dy dx equals 2x minus 3y squared dy dx. And then we'll gather everything to one side that has a dy dx and everything that doesn't to the other side. So that's going to give us 2 minus 2x equals, we'll bring the 3 over there, 3 dy dx minus 3y squared dy dx. Everybody good so far?
Yeah.
And then we factor out the dy dx, and what are we going to end up dividing by?
3 minus 3y squared.
3 minus 3y squared. So there's our derivative. We want to know when this has vertical tangent lines, so when it's undefined, so when the denominator equals 0. So 3 minus 3y squared equals 0. Okay. This would be vertical tangent lines when dy dx is undefined. So we just solve this. That gives us y squared equals 1, right? Or y equals positive or negative 1. So that's telling us y values at which we have a vertical tangent line. Well, vertical tangent lines, what do their equations look like? Or any vertical line for that matter. Any vertical line has an equation that looks like what?
X equals.
X equals something. So I've got y equals something here. So what do I need to do to figure out what x equals? Any thoughts?
Could you plug it in?
Yep, we got to go take it, plug it back into our original equation. So we'll substitute y equals 1 for all the y's and get an x value, and then substitute y equals negative 1 in for all the y's and get an x value. So if we plug in y equals 1, that's going to give us 2x minus 3 equals x squared minus 1. And if we plug in negative 1, that's going to give us 2x plus 3 equals x squared plus 1. Everybody agree with those?
Yes.
Okay, so I think I should make a note here. This is y equals negative 1. This is y equals 1. All right, so now we'll just solve both these quadratics. So this one becomes x squared minus 2x, right? And then minus 2. And this one becomes x squared minus 2x plus 2. And how do we solve those? Neither of them factor nicely, right? So it's either a quadratic formula or completing the square. Probably easier to just complete the square on them. So we'll do that here first. So this is x squared minus 2x equals 2. And then what do we need to add to both sides? How do we complete the square of that?
A positive 1 or negative 1.
Positive 1. Half
Positive.
of this value, half of negative 2 is negative 1, and then squared is positive 1. So we add 1 to both sides. This should then factor. And we get x minus 1 equals plus or minus root 3. And x equals 1 plus or minus root 3. Then over here, well, what's the problem with this one? This one has no real solutions. Why does this one have no real solutions? Well, if I were to do the same thing, right, we'd subtract the 2 over here. We have x squared minus 2x equals negative 2. And then when we added the 1, we have x squared minus 2x. Well, let's factor. We'd have x minus 1 squared equals negative 1. And then when I square root, I don't get any real solutions, right? Can't square root negative 1. Everybody agree with that or no?
Yes.
Yeah.
All right, so these are our only potential solutions, x equals 1 plus root 3 and x equals 1 minus root 3. We have to make sure of one other thing. So we have to make sure that the x and or the y values don't make the derivative indeterminate. So if I were to plug in y equals 1 or y equals -1, we know that makes the denominator 0, but we have to make sure that these x values that we got don't also make the numerator equal to 0. And I think it's pretty clear that the only value that would make this numerator equal to 0 would be x equals what? 1, right? And neither of those are x equals 1. So these are definitely our solutions. And if we were to graph this on Desmos, let's see, what was our original equation? It was
2x minus 3y.
2x minus 3y equals, what was it, x squared or something minus
X squared minus y cubed.
y cubed. Right? So we got this little hyperbola looking thing here. And we had
You forgot one of the y.
y cubed. There we go. We got this fun looking thing. And we ended up with x equals 1 plus root 3. And there it is, tangent, vertically tangent right there at this point. And if we do x equals 1 minus square root 3, we got the furthest most point over here where we have our tangent line as well. Everybody good with that? All right, no questions? Everyone's all right?
Yeah.
All right, let's see if we can work through another one real quick here. So taking the derivative of this one ought to give us what?
4x minus 12y squared equals
12y squared dy dx.
dyx equals 3x squared minus 2y times dy over dx.
All right, and now we'll need to solve that for dy dx. So we'll maybe subtract the 3x squared, and then we'll add the 12y squared over, and those both have a dy dx in them, so we can factor that out, giving us 4x minus 3x squared over 12y squared minus 2y is our dy dx value. Everybody good with getting dy dx there?
Yeah.
All right. So we want horizontal and vertical tangent lines. For the horizontal tangent lines, we need to set the numerator equal to 0. Somebody's not muted. There's a bunch of background noise. If you can mute yourself, if you're not. Thank you. So we got a horizontal tangent line will be when the numerator is equal to 0. So let's solve that. What can we factor out of there?
X.
Factor out x. X times 4 minus 3x gives us values of x equals 0 and x equals, we do that, 4 minus 3x equals 0, right? That ought to give us x equals what? 4
Over
thirds.
3.
Yep. So x equals 0, x equals 4 thirds. And then to look for vertical tangent lines, we'll do this one over here. We need to set the denominator equal to 0. So that'll be 12y squared minus 2y equals 0, which when we factor out a 2y, right, gives us 6y minus 1. And that gives us y equals 0. And it gives us y equals 1/6. Everybody all right with that?
Yes.
All right, cool. So if I were to plug in x equals 0, what would I get out as my y value? If I plug in x equals 0 up here, what do I get? 0 minus 4y cubed equals 0 minus y squared, right? Or 4y cubed minus y squared equals 0. Everybody agree with that? How do we solve that? What do we factor out of that?
The y squared.
We factor out a y squared. So y squared times looks like 4y minus 1 equals 0. And what does that give us? Y equals 0 and y equals 1/4, right? So what do we notice? That one of the points that we end up with is the point 0, 0. True?
True.
Okay. So that point 0, 0, right, we end up, I'm going to write these out. We get 0, 0, and we get 0, 1/4. Well, 0, 0 would make my derivative indeterminate, right? If I plug in 0 for x and 0 for y, I end up with 0 over 0 in my derivative. So this is going to be no vertical tangent line or horizontal tangent line for 0, 0. But the point 0, 1/4 ought to have a horizontal tangent line. Okay? So we got to end up with that one is y equals 1/4. Everybody good with that so far?
Yes.
All right.
Why is the x value 0 for like both like possible horizontal tangent lines?
Sorry, say that again. Why is the x value 0 for both of them?
Yeah, like so there are like two possibilities, like 0, 0 or 0, 1/4. Why is
Well, there's more also. We're also going to use x equals 4.
Oh, okay.
Yeah, so these are the possible x values at which we might have horizontal tangent lines. So we've done it for x equals 0 and got 0, 0 was 1 point and 0, 1/4 was another point. But we still have to do the 4/3. Yeah.
Okay, yeah.
Okay. So now when we plug in our 4/3 up here for x, 4/3 squared ought to be 16/9, right? Times 2 is 32/9. Minus 4y cubed. This is going to be a little bit of a pain now. 4/3. If we cube that is what, 64/27 minus y squared. And we end up with 4y cubed minus y squared. And then that's going to be minus 32/27 in the end there. Equals 0. Now that's going to be a pretty difficult equation for us to just solve by hand. True? You
Yes.
agree? Anybody know a good way to solve that? I mean, I do, but it's not real pleasant. I wouldn't call it a good way to solve that. So how can we find when that's true? Well, we can use our graphing calculators to graph that equation and see when it crosses through the x-axis. So I'm going to do that in Desmos just so I don't have to open up my other calculator. You guys all remember how to find x-intercepts using your graphing calculator? Hopefully, from like way back when you did that a long time ago. in like integrated 3 or something? No? Do you remember how to do that or no? Have you ever learned how to do that? You're all awfully silent. Well, we're going to have a whole big thing about how to do that eventually. So, all right, we end up with, looks like it comes out to be 0.761 approximately is where that crosses through. So we're gonna work on how to figure that out on your graphing calculator when we do some of our applications of derivatives. But for now, that solution to that equation is 0.761. So this is y equals 0.761. Everybody okay with that or no?
Yes.
All right, then we still got to do the same thing for our vertical tangent lines. And we're probably going to need a new page for that. So if we plug in y equals 0, what is that going to give us? Y equals 0 is going to give us 2x squared equals x cubed. Or x cubed minus 2x squared equals 0. Or if we take out the x squared times x minus 2 equals 0, and we get x equals 0 and x equals 2. And once again, this x equals 0, 1, 0, 0 isn't going to work. But x equals 2 should, right? Because x equals 2 was not one of the solutions that we got for making the other part of our derivative equal to 0. So we got a vertical tangent line of x equals 2. And then we also need to use y equals 1/6. That was our other value, right? So we're going to have 2x squared minus, what was it, 4y cubed? So 4 over 216, which is what? 2 over 108, which is 1/54. And then we're going to have equals x cubed minus y squared, and y squared was 136. And so this one ends up being another unpleasant cubic, x cubed minus 2x squared. Let's see, what's 136? Or what, yeah, negative 136 plus 154. Anybody know what that is off the top of their head?
5 over 108. I think.
I think it's going to be maybe 1 over 108. Yeah, that's going to be minus 1 over 108 equals 0. And so if we solve this equation, we can do the same thing with Desmos. So x cubed minus 2x squared, now it's minus 2x squared minus 1 over 108. So that one, if we zoom in here, almost looks like it's crossing there, but it's not. Crossing at 0.5089. So that will be our other value here. X equals, what did I say, 0.5089? And that should be our other vertical tangent line. Yeah, 5089. Cool. So everybody conceptually okay with all of that?
Yes.
All right, so let's graph this equation. What was our original equation?
Two x squared
2x squared minus 4y cubed
is equal to x cubed minus y squared.
Sorry, is equal to what?
X cubed minus y squared.
X cubed minus y squared. All right, so here's our graph. And what were all of our different tangent lines that we had? We had y equals what? We had two different ones for y. Y equals
1/4.
1/4. All right, there's that one. Right there at the little bottom right there. And the other one was y equals 0.761, is that you said? And that was an approximation, but if we look right here, we can, if we zoom in right there, there it is being tangent right there. And what about our vertical ones? We should have had, how many of those did we have? We had x equals 2 was one of them, right? So that's that one. And do we have another one or no?
X equals 0.5089.
0.5089. That doesn't seem right. That one doesn't work. Yeah.
I think when you did the graph for that last vertical tangent, or vertical as whatever it's called, you did 4x cubed instead of just x cubed.
Oh, that would be a huge problem. All right, so it should be x cubed minus 2x squared minus 1/108. Oh yeah, that comes out to be 2.002. I just did that on my other calculator. X equals 2.002. So that's very, very close. Oops. Very, very close to this other one at x equals 2. So we got two different ones that are right there on this place where it looks like it's becoming vertical. So it must become vertical for a second, become not vertical for a second, and then go back to being vertical again. Right there, right around 2. Okay. Everybody good with that?
Yes.
All right, cool. All right, we're going to do one more of these. We're not actually going to find all of the tangent lines this time. We're just going to find out where they occur. This one's going to get a little bit more difficult even than the last one. So first thing we're going to need to do is take a derivative. What's the derivative of the 2x squared? Should be 4x. And then our minus 2xy, that's a product rule. So minus 2x times the derivative of y. And then the derivative of minus 2x is minus 2 times the y. And then plus 2y dy dx equals 0. Everybody okay with that?
Yeah.
All right. And what does that leave us with here when we get everything to one side with the dy dx? It gives us a 4x minus a 2y equals 2x plus 2y on the other side. Sorry, 2x minus 2y on the other side times dy dx. And then we'll divide by the 2x minus the 2y. And end up with this. And we could simplify that down. We could divide everything by 2. So 2x minus y over x minus y will probably make things even a little bit easier now. Everybody okay with that?
Yeah.
All right, so good. What's different about this one? when I look for the horizontal and the vertical tangent lines,
There are X's and Y's in both the numerator and denominator.
yeah, I got X's and Y's, so that's going to complicate things a bit, huh? Our horizontal tangent lines will come from 2x minus y equals 0, and our vertical tangent lines will come from x minus y equals 0. So this one just tells me that x is equal to y, and this one tells me that y is equal to 2x. Yeah? Well, how do I go about figuring out when x equals y or when y equals 2x?
You could substitute back into the original equation.
Exactly. We're going to have to substitute back up into the original equation. So we're only looking for the locations of where these occur, which means we're going to want everything to be in terms of x values, probably. So if we substitute y equals 2x in, that ought to work out, right? So we're going to plug this in. Y equals 2x, that'll give us 2x squared minus 2x times y, which is 2x, plus 2x squared, and then I'm just going to say equals 4. I'll add the 4 to the other side. And what do we have here? We got 2x squared minus 4x squared plus 4x squared, so that's just 2x squared equals 4, or x equals plus or minus root 2, where we're going to have horizontal tangent lines. Good or no?
Good.
All right. And what about over here? If y equals x, we can just plug in x for the y's, right? So we're going to plug this in. And that'll give us 2x squared minus 2x squared plus x squared equals 4. And that'll give us x equals plus or minus 2. Everybody agree with that? The 2x squareds cancel. It's just x squared equals 4.
Yes.
Cool. All right. So we go back to Desmos here. Let's see. I think I remember this one. This one was 2x squared minus 2xy plus y squared equals 4, or minus 4 equals 0, right? It should be an ellipse. Yeah, there's our ellipse. And we ended up with x equals 2 and x equals negative 2 as our locations of the vertical tangent lines, which are just our vertical tangent lines. And then we also said that x equals square root 2 is where the horizontal one would be. And it sure looks like that's where that horizontal one would be, isn't it? And x equals negative square root 2 will be where the other one was. If we wanted to figure out what those actual values were for those, what those actual y values were, could we do that? I know it didn't ask us to, but could we?
Yes.
Yeah, we definitely could. How could we do it?
Plug in both of those, all those x's.
Where would we plug in x equals root 2 and negative root 2?
Could we plug them into the vertical tangent and horizontal tangent line equations?
We could plug them in right here. We could also plug them in back up here. But if we plug them back up in here, that's going to be a more complicated equation to solve. But this one should also be true. So we should get y equals plus or minus 2 root 2 as the actual equations. And so then if we go back to Desmos and put those in, y equals 2 root 2, there's that one, and y equals negative 2 root 2, there's the other one. Good or no? So those are our points where we have these horizontal and vertical tangent lines. Any questions, issues with any of that? Everybody okay there? Any problems with that? All right. Now let's see if we can find a second derivative using implicit differentiation. What do you think we need to do to find a second derivative before we can find the second derivative?
Find the first derivative.
That's right. So finding the first derivative. Do that. That should be the easy part. We've done that a bunch of times, right? So derivative of the x squared is
2x plus 2y times dy over dx equals 1 minus 1, or 1 dy over dx minus 1.
Everybody good with that?
Yeah.
All right. So now we need to get our dy dx by itself. So 2x plus 1 equals dy dx minus 2y dy dx. Factor out the dy dx. We got 1 minus 2y. And we got dy dx equals 2x plus 1 over 1 minus 2y. So far, so good?
Yeah.
Okay. Now, to find our second derivative, all we have to do is take the derivative of this. The second derivative ought to be the derivative with respect to x of 2x plus 1 over 1 minus 2y. And how do I find the derivative of that fraction there?
Quotient rule.
Quotient rule. So it should be 1 minus 2y, right, our denominator, times the derivative of our numerator, which is 2, minus the numerator times the derivative of our denominator. What's the derivative of our denominator? With
Negative
respect,
2.
not just negative 2. Remember, we're taking the derivative of 1 minus 2y with respect to x.
dy
So-
dx.
Right, negative 2 dy dx. And then all over 1 minus 2y squared. Everybody get why we have to attach that dy dx to the negative 2 when we do the derivative of the denominator?
Yeah.
Okay, cool. So this looks like a good answer, but it's not a good answer because we don't want to ever have a dy dx in our final answer for the derivative. So how can I replace this dy dx?
The derivative already found.
Yeah, it's the derivative I already found. Exactly. So this should now become, let's see, 2 minus 4y minus, well, let's see, we'll call this, since I got a negative 2 in the negative, we'll call this plus 2 times 2x plus 1 times that dy dx. Good or no?
Good enough.
All right, this is simplified enough for my liking, but if it's not simplified enough for your liking, you can always get a common denominator. This 1 minus 2y is already being multiplied by all of these things, or dividing by all of these things. But if you want to, you can make this multiplied and divided by 1 minus 2y and then drop the 1 minus 2y into the denominator. Which would give us, in this case now, 1 minus 2y times 2 minus 4y plus 2 times 2x plus 1 squared all over 1 minus 2y cubed. So either of those answers would be fine. I would accept either one of those. Or you could even distribute out the whole numerator if you wanted to. That seems unnecessary though. Everybody okay with that? Any questions with that?
No.
All right, let's do one more of these, and then we're going to be good on implicit differentiation. We'll have talked about everything with implicit differentiation, and we'll get into some of the other methods we'll use to take derivatives today, and then finish those up tomorrow, and we'll be off to a good start in the first 3 weeks of this quarter. So first thing we need is the first derivative. So we'll take the derivative of both sides with respect to x. The xy becomes x dy dx, and then plus y times the derivative of x. Everybody good with the product rule on xy?
Yes.
Okay. Minus 2y dy dx minus 1 equals 0. And we'll bring the positive or the negative 1 over here as a positive 1, and the y over as a minus y. And then we can factor out the dy dx here from the x minus 2y. And get our first derivative. Everybody good with the first derivative?
Yes.
Second derivative then, we will use the quotient rule, and it's still implicit differentiation. So we're going to have x minus 2y times the derivative of 1 minus y. Well, that should just be negative dy dx minus 1 minus y times the derivative of x minus 2y, which is 1 minus 2 dy dx, all over that denominator squared. Good or no?
Good.
Cool. And then we just got to replace all the dy dx's with what dy dx is. So our final answer should be x minus 2y times negative 1 minus y over x minus 2y minus 1 minus y times 1 minus 2 1 minus y over x minus 2y all over our x minus 2y squared. And I don't need you to simplify any further than that. I would accept that answer. If you really, really wanted to put an x minus 2y underneath everything and drop it down, all you'd have to do is multiply this 1 by x minus 2y over x minus 2y and combine the numerators, and then you could do it, but I'm good with that. Any questions, any issues, any problems with any of the implicit differentiation stuff? So we're going to move forward into derivatives of exponential functions like e to the x or 2 to the x or 7 to the x power or something like that. But before we do that, we're going to take a look at this function right here. F of x equals e to the x minus 1 over x. What does it appear that the limit as x approaches 0 of e to the x minus 1 over x is?
1.
Sure looks like it's 1, doesn't it? Right? I will tell you this is true. There's a really easy way to prove it. that we don't know yet, that we'll learn when we start doing applications of the derivative. But this is a true statement, right? The limit as x approaches 0 of e to the x minus 1 over x is 1. We're going to need that in the future. So just keep that in the back of your head as we try to find a way to get the derivative of e to the x. So how are we going to get the derivative of e to the x? Do you know the derivative? It's not just a power rule problem, right? Power rule would be x to a power, right? If I had x to the e, I could take the derivative of that. That'd be e times x to the e minus 1, right? Because e is just a number, right? But I don't have that. Say that again?
X times e to the x minus 1.
So that'd be using the power rule, right? Unfortunately, that doesn't work. The power rule only works when it's the variable to some number up there. So we can't do that. Power rule is only good for variable to a number. This is number to a variable. So let's think back to sine of x. What do we do with sine of x when we didn't know its derivative?
A substitution.
We didn't do a substitution with sine x. We did a
Limit.
We did a limit. We did a limit as h approached 0 of the difference quotient, right? E to the x plus h minus e to the x all over h. Isn't this the limit definition of the derivative? So I should be able to find any derivative by using this limit of the difference quotient. So what can I do with that now?
Split up the e term, the e to the x plus h term.
This term, how do you want to split that up?
Since it's x plus h, you could do e to the x times e to the h.
Wonderful. Brilliant. That's wonderful. Yeah, e to the x plus h is e to the x times e to the h, right? Same base, you add the exponents. So I could just go the other direction. And what does that allow me to do?
Factor out an e to the x.
Factor out that e to the x. So we now have a limit as h approaches 0 of e to the x times e to the h minus 1 all over h. And what do you notice now? What do you notice now? What do you notice?
It's the same as the last slide.
Ah, it's the same as the last slide, except instead of x's, we've got h's. So I could separate this into two different limits, one for e to the x and one for this limit that I now know from the previous page. And to what's the limit as h approaches 0 of e to the x?
E to the x.
Just e to the x. And the limit as h approaches 0 of e to the h minus 1 over h, as we just found, is 1. And what's 1 times e to the x? It's just e to the x. Wait a second. You're telling me that the derivative of e to the x is e to the x? Yep, that's true. The derivative of e to the x is e to the x. Guess what the second derivative of e to the x is?
E to the x.
Guess what the 1/1,000,000th derivative of e to the x is? It's still e to the x, right? The derivative of e to the x is e to the x. Everybody good with that? That's a derivative you want to know and memorize. Now, it should be easy to memorize since you only have to remember one function, e to the x. Besides putting like a constant in front of this, like 2 e to the x, and then taking the derivative of 2 e to the x to get 2 e to the x, right? There's one other function that when you take the derivative of it, you get the same function that you started with. What is that function? Nobody? Usually people come up with the answer to this right away. There's two functions. What is it?
Is it any constant to an x?
No, no, no. A constant times x would be, you mean to the power of x, you
To the
mean?
power of x, yeah.
Yeah, no, unfortunately, those ones don't work out as nicely as e to the x does. It's a really, really simple function that we've already dealt with.
Y equals 0.
Y equals 0, right? Take the derivative of 0, you get 0, right? That's the other one. So e to the x and 0 are the only functions that when you take their derivative, you end up with the same thing. But this is very important. The derivative of e to the x is e to the x, right? Derivative with respect to x of e to the x is e to the x. Now, we could apply the chain rule with this. So instead of having just e to the x, I might have e to a function, right? In which case, the derivative will just be e to that function times the derivative of that function. So this is just the chain rule application of the new derivative for e to the x that we've just learned. Good or no? So this right here is y equals e to the u, with u equal to x cubed plus 5x. So if I want the derivative of e to the x cubed plus 5x, it ought to be e to the u times the derivative of that, which is 3x squared plus 5. Or we ought to get 3x squared plus 5 times e to the x cubed plus 5x. Good or no?
Good.
All right, what about this one? Y equals e to the x squared plus sine x. That's just y equals e to the u with u equal to x squared plus sine x, right? So what's the derivative of x squared plus sine x? That ought to be
2x
2x
plus cosine x.
plus cosine x times e to the u. So taking the derivatives of e to a power, actually, those are pretty easy derivatives, actually, yeah? Everybody okay with those or no?
Yeah.
All right. What if it was a to the x instead of e to the x? Any thoughts on how we would do that?
Wouldn't it just be a to the x because a is going to be a constant like e?
Unfortunately, it doesn't work out that way. This rule is only good if the base is e, because specifically of this limit right here. A to the x minus 1 over x doesn't have a limit of 1, unfortunately. So it would have to have, a to the x minus 1 over x would have to have the limit of 1 for this to work out nicely. And it unfortunately does not. So we're going to have to find a little bit of a workaround for this. we are going to use the derivative of e to the u, right, or e to the x in this. So is there a way to rewrite a to the x as a power of e? Let's start with an easier question. Is there a way to rewrite 7 as a power of e? Just some number. What goes in the parentheses? You must have somewhere along the line learned something about e and powers of e. You had to have. Isn't that the same thing?
Yeah.
Have you seen that before?
Yes.
Yeah, okay. These things that you've seen before are important. You have to remember them. So 3 is e to the,
Natural log of 3.
and x is e to the natural log of x. So what is a to the x? A to the x ought to be e to the natural log of a to the x. Everybody agree with that? These things cancel each other out, right? If we want them to. We don't want them to because we know how to take the derivative of e to a power. Is there a way to rewrite natural log of a to the x using log rules?
E to the x times the natural log of a.
Exactly. Anytime it's a logarithm of something to a power, you can take the power and pull it out in front of the natural log. And so e to the x ln a. And so now what do we have? We've got y equals e to the u, with u equal to x times the natural log of a. All right. Well, how do we take the derivative of this? What do we do here? The derivative of e to the u is e to the u. And what about the derivative of x natural log of a?
Do we have to use the product rule?
You do not need to use the product rule. We could use the product rule if you want to, but we don't need to. What is natural log of a? What is a?
A constant?
It's just a
Greater than
constant, right? It's just some number, right? What's the natural log of some number?
The
Some
number.
other number, isn't it? So what am I looking at here? I'm looking at some number times x, right? Suppose that's 7x. What's the derivative of 7x?
7.
7.
The derivative of 3x.
3.
What's the derivative of pi x?
Pi.
Pi. What's the derivative of any number times x? It's just that number, right? So natural log of a is just some number. So what's the derivative of natural log of a times x?
Natural log of a.
Okay.
The natural log of a. And then if we go back through here, what's e to the u? Well, e to the u is e to the x ln a, right? Well, what's e to the x ln a? Well, that's e to the ln of a to the x. Well, what's that? That's a to the x, isn't it? So I can replace e to the u with a to the x. Everybody see that and is okay with that or no?
Yes.
Okay. So our derivative of a to the x is just a to the x times the natural log of a. And really, if we think about what's the derivative of e to the x, well, we know it's e to the x, but if I were, e is a number that's greater than 0 and not 1, right? It's like 2.87, 287, 288, something, 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 right? If we think about this, couldn't I apply this derivative using this specific rule with the base as e should be e to the x times the natural log of e. Well, what's the natural log of e?
1.
1. So this just says the derivative of e to the x is e to the x. Right? E is just a special case of this a to the x rule. Good or no? All right. Could we apply the chain rule to this also, this derivative of a to the x? Make it a to the u? Yeah, we could. All right, so if I had a to the u, the derivative ought to be a to the u times the natural log of a still, and then times the derivative of u. So let's do a couple of these and then we're going to be good for the day. This is y equals 3 to the u power with u equals sine x. This is just the chain rule. So the derivative of 3 to the u is 3 to the u times the natural log of 3, and then times the du, which is cosine x. And so we end up with 3 to the sine x, natural log 3, cosine x. Good or no? Any questions or issues with that? You all still alive out there? Everybody all right? We only got one problem left to do. How do we find the derivative of 7 to the x squared cosine 5x?
Turn x squared cosine 5x to u. And then
All right, so now the 7 to the u is 7 to the u times the natural log of 7.
yeah.
I'm going to write 7 to the x squared cosine times the natural log of 7 times the derivative of x squared cosine 5x. Well, what's that? That should be
2x
squared.
times, yeah, actually, yeah, 10x times negative 10x sine x.
No, this is a product of two functions. So this has to be done using the product rule. So we've got x squared times the derivative of cosine 5x. Well, what's the derivative of cosine 5x?
Negative 5 sine x.
Negative 5 sine 5x.
Oh, yeah.
Plus 2x cosine 5x. There's the product.
Yeah, all right.
So our final answer, if we wanted to simplify ever so slightly, would be negative, pull that negative 5 out of there. Negative 5x squared sine 5x plus 2x cosine 5x. Any questions on that? Everybody good? No questions.